So this week we got more in depth into this uh, coherent detection and mostly balance detection. What kind of uh, structures we use to detect uh, these coherent signals? What is the state of the art that was shown this week? So the first three videos were, I think, based on this balance detection and concepts related to that. And the last three lectures were based on what are the digital signal processing steps that are common in like today's communication systems. So that second part went really fast, I think, but you can pause and look at codes also. I am also making a copy of the code, but that is still like pending. All of these things are pending. Uh, there are a couple of codes I have to share with you, and um, text transcripts. I don't know. It probably won't be there in time. Anyway, we started this week with a quick recap of coherent detection. What was covered when we were discussing this photodetector noise and all these concepts. Then we went on to discuss this balance detection using uh, these 2x2 couplers and how to adapt that same structure by uh, using polarization beam splitters. I think polarization beam splitters were not discussed during the components week last week, I think. But I hope everyone got the concept. It just separates the X and Y fields, you can say. So we use polarization diverse balance detection, how it is done, and we had some uh, phase lock loops were used for one structure. And to avoid that and do everything in optical domain, we introduced this concept of 90-degree hybrid, which was a modification of the uh, balance detection structure we used. Then we went on to uh, touch on the impairments and how to deal with them. So laser line width was discussed during the laser week 3, I think. Then dispersion, which is here we are calling it chromatic dispersion because wavelength dependence is the thing we are talking about. So single mode fiber wavelength dependent dispersion. So uh, we're calling it chromatic dispersion. Then uh, what were the other? So then how to this uh, how to do carrier phase recovery, which is uh, after each symbol you correct for the phase that is accumulated. Then frequency offset correction using this uh, fourth power of the signal that was discussed, and how polarization demultiplexing is used. And we briefly touched upon this constant modulus algorithm. We don't need to go too much in depth into this, but I hope the concept was clear, like how the constellations change and how we try to balance the two powers and make basically constant modulus algorithm tries to make the modulus constant. That's all. And we ended with this flowchart of how the DSP process, the different DSP algorithms are applied at the end. So there was a flowchart shown. There were a lot of diagrams and uh, a lot of formulas, but they were not very complicated. I did not go ahead and draw all of the diagrams again. I hope you took notes. So the final flowchart we discussed was this: how to like resample whatever the ADC gave us, then chromatic dispersion compensation. We did not discuss too much into it, but we discussed it before a couple weeks ago, I think. And code snippets were shown. Then frequency offset correction, digital clock recovery. I think you'll be more clear when we share the code for this week. And then polarization demultiplexing, uh, then carrier phase estimation, and then you can take the decision and calculate this bit error rates and all these things. I think Harshita asked a couple of questions. I did not answer. Sorry. So in this assignment, so you're given the transfer function for this 90-degree hybrid. Just use this and follow whatever steps we used in our class also. But this is not balance detection. It's just asking I1 and I2, and then it's asking like what is the square of AC components. The same thing is to be applied again in this other transfer function, but here only use port 1 and 2. So this so these first four terms are the only ones you have to use. Ignore the third port, the input third port you have to ignore, and also the output third port you just ignore it, and you repeat the same process for this other transfer function that is given, like this matrix is given. And for SNR, so all of these, whatever we are arranging, these are in this optical domain. So at the end of it, we will apply this, we'll detect using our photo detectors, and most of the noise will come from that. So when you are asked to like compare the SNRs of the two values, like just see how the signal power has changed and assume that noise has remained constant. So for example, you get some expression like this. You compare this signal power to what would have been the other case. Like, here we are asking you to compare the 3x3 coupler, which in the case with ideal hybrid. So just find the ratio, and here they are asking you to just answer in dB scale the ratio. So I think that's the entirety of the assignment. I don't think it should be too difficult. But if you have any thoughts, you can say. Harshita asked about this question, I think, a long time ago. I forgot to answer. Let me get my writing device working, then I'll present again. Ashok can start, and then let me get my Wacom working.
I'm having one doubt.
Yes, yes.
There's actually coherent homodynamic deduction with a 90-degree hybrid in that um, del of IT at why I4 minus I3 is done there, sir. I cannot understand that part.
90-degree hybrid, and del I is calculated, and then
Everywhere we are calculating from 1 to 2. Why we are calculating in that part I4 minus I3?
right, I did not think. Okay, let me check.
Okay, sir.
Any other questions, class? Have you any doubt? You can put your doubt in the chat box also if you want that. If any problem in unmuting
Sir, question number 7, 6, and 8, sir.
for assignment.
Yes, sir.
Okay. Jonek already explained regarding that, I think that. 6 is that 3 into 3 couple of 90 degree that questions. Hello?
Yes, sir.
That question one way to realize 90 degree hybrid to use 3 into 3 coupler and that input. That one.
Yes, sir.
So matrix you have to already given, you have just that yes, Akansha, we will do. I will do that. Anything other else then? So anyone can me tell that what is the issue with the heterodyne detection? So we have to go for the balance detection because in the receiver we use the heterodyne detection in the communication, optical communication. But now we have to move to the coherent balance detection or that. So what is the problem with the heterodyne receiver detection? So that's why we have to go to balance detection. Anyone can. Please participate in that. Otherwise, I will also not just to solve that problem and then I will get. Whatever you know that you can tell us that. No issue, it is wrong or right that.
Sir, it is close frequency, those are mixed with the result signal with the intensity, which is directly proportional to the true signal.
Okay. Any other?
So there is both radiation, electromagnetic radiation, as well as optical radiation.
Okay. What is happening in case? Let's we have the one signal. That signal will be fed to, there is a one beam combiner, that optical component, there is a one local oscillator, okay, and then it will be combined here, that phase will be combined, both the phase is here, and there is a photodiode detector, and there is a one amplifier which amplify that current. So what is that output current? IP is directly proportional to ई सिग्नल प्लस ई एल ओ टी का होल स्क्वायर. E signal means intensity of that signal. LO means ELO means that intensity of that local oscillator that combined with that signal. So it will generate some noise. We did not require that thermal noise, short noise, or anything noise will be less in that our communication system. So its signal have a frequency omega s. It have the frequency omega l. So what is the happen that IPT at output of the photo detector we have represent at E into R, I into R square like that current. So it have the power signal of that PS signal PLO plus 2 root square PS PLO cos omega st minus omega lt plus phi. So what is happen? PSPL2 it is a DC term. It is constant and it should be negligible. If it will be increased, that IPVT will increase and the photocurrent will be saturated. In that case, we do not bother saturation in that case. It will be saturated and it will not detect any signal in that case. Another term is that we have the cos omega t and omega lt. Okay. Omega st is the signal frequency and omega L2 is the local oscillator frequency, and phi should be the phase. So what have been happen that if the phase of that local oscillator signal and our original signal, if will not be same, or either it will be the orthogonal, then we have to receive the minimum signal at the outside of the photodetector. So phi should be same in that case also that. So what is happen in the heterodyne receiver, that these problem are happen in the heterodyne receiver. That's why we have to go to the balance detection. Have you understand?
Yes, sir.
I need your input also that. If anyone want to add anything, then you can add. So this is the diagram. I have already explained that. This is the current. So what DC term are usually neglected, but many cases interface. This term is all we have already neglected, but some interference at the intermediate frequency. IF is the intermediate frequency. So this signal is that omega s, and there is a signal, it is omega l. So what of this signal, both will be combined in that combined bit, and if they have the same phase, this may be that omega s, omega l, this is omega naught frequency. So there is an intermediate frequency in that case. So it will be role in play of that in that case. So we cannot distinguish that whatever the original signal frequency and what is that local oscillator frequency. So some interference in the intermediate frequency will happen in that case. Secondly, large photocurrent may be due to that strong local oscillator. I already explained that PSPLO. Result in the low saturation amplifier after the photodiode. Polarization of input signal and low signal should be matched. That phi should be same. Otherwise, it will be minimum current. Why polarization control used in with local oscillator in the optical receiver? In the balance detection, why we use the polarization control with the local oscillator? Anyone can answer that? And whatever the basic component for the balance detection? Why we use the polarization controller? Class, Akansa? So what is happen in that case? If I draw the schematic diagram of that, like that, this is the our ES signal. We have the 2 into 2 coupler. So this basic component of that for balance detection is 2 into 2 coupler. So this is my local oscillator, and this is my PS signal. This is my ELOT signal for this EST and ELT. Then this coupler will be divided into two modes. There is photodiode. Both photodiode will be have the same property. So one is E1T, another is E2T, and then we have combined this signal here, both signal, and this is I1T. So question asked by the student, how can we delta T and delta I1 have to calculate it? They have many one have that doubt. I think that. So
Sir, it can modify the polarization state of light.
no, why we polarization controller? Because it will be we have the two signal. We have E1 and E2 in that case. In the local oscillator, we have the maybe frequency or that noise, thermal noise will be more in that case.
Yes, sir.
So we have to minimize that thermal noise, or we not required with the thermal noise, but oscillator will be generate a thermal noise. So what is happen that EST equal to our signal will be AST into e की power j omega st plus phi s. Sorry. So what is AST is the amplitude of the signal, omega s is the frequency of that signal, and phi is the phase of that frequency. Okay. So every signal has some phase in the time domain. It will be if it will be phase modulation signal or coordination phase modulation signal. So it has the every time the signal will be change its phase with the time. And what is ELO? ELOT equal to same is ALO e की power j omega LOT plus phi LO. So it have this it has also some signal. So what happened that I have already explained that previously that heterodyne receiver there is some intermediate frequency. So omega f should be omega s minus omega L0, and delta phi change in the phase should be phi s minus phi LO. So we assume that signal and local oscillator are in the same polarization, means it have the same phase, same frequency, same amplitude, and there is no change in the phase, signal in that amplitude. So if we take that matrix, so now you have to define it how to calculate E1, I1 and I2. You have to understand from this diagram also. So my signal should be there is a one is E1 T come to after 2 into coupler, and one is come to E2 after 2 coupler. Okay, that should become that 1 bata root 2 matrix. 1 J is the change in the phase, that imaginary component, and J and 1. And there is a one signal that this is EST and one is the ELOT. Okay, understood? So if you multiply these two matrix, it will become 1 upon root 2 EST plus J component of the ELOT, that imaginary component, ELT plus J component of the EST. I am correct? Hello? Hello?
Yes, sir. Yes, sir. Yes, sir. Yes.
Akan sir, are you here? Or you left? Okay. So, what is my I? I equal to E into R, V into R. Some basic formula. Here V is our signal intensity and R is there. So, what is happen that when I calculate the I1 and I2, what is happen in that case? Can anyone be answer that? So my I1T, I2T, it should be equal to, because we have the 1 by root 2 square E1 and E2, root 2 and root 2, that will multiply by 2, and this will be root RD by 2, and we have the mode, because we have take the mode, so we have to take square of that 2, that E1ST plus J EL2 EL2 plus J EST, that's it whole square. because you take the mode and take the whole square of that. That's why this component will be RD by 2. So we have to put the value of the ES1T and EL2 that previously that I have mentioned, that AS A2 e to the power j omega st plus phi, and ELO2 equal to ALO e to the power j omega LOT plus phi LO. So what happened then, we have to put that value of the in place of the even ES2 plus ALO GT. So it will become mode of AOS T का square plus ALO T का square, because you have to take a mode, so it minus J square ALO square should be 1 minus 1 plus 2 times AS ALO sin omega intermediate frequency T plus delta phi, and second component should be same AST का square plus मोड का होल स्क्वायर माइनस, बिकॉज AS T ALO sin omega intermediate frequency T plus delta phi. So from that you can calculate I1 and I2 in that same case. So what will happen, how to calculate delta IT, delta I2 equal to I1 minus I2 in that case. So if we subtract this I1 and I2, this will be gone, these both things will be gone, because minus minus 2 component will be subtract. So we remaining only with RD by 2 and RD by 2. So it will be 2 it will be plus 2 and plus 2 4 plus 2 is divided by, it will be 2 RD remaining, and we have to remaining AS and ALO, that imaginary component, sin omega T plus phi f. Okay, so if we in the place of that AST and ALO, just we put that amplitude of that signal, so it will be PST and PLA square, the variance we take that amplitude variance, signal variance. So it will become around 2 RD underscore PST PLO sin omega IT plus delta phi. So from this matrix you have to remember that first matrix E1 2 and E2 2. From that you have to just multiply that ES1T signal and ELO signal, and then you have to calculate E1 and E2. Any doubt in this?
Sir, can you repeat the last two term?
So you have to calculate I1 and I2, that formula you just take them amplitude and multiply that. That part is okay? Hello?
Okay, sir.
Now you have to calculate in the output side of the balance code direction delta IT. So delta IT should be that I1 minus I2. So what is happen, that if you subtract that I1 and I2, that matrix you have to calculate. So DC component will be subtracted, because they are, one is positive, both are the positive, so one will be going negative side. So it will be cancel, both cancel. But what happens side, that in the that imaginary side component, that 2s2, one is the positive and another is negative, so both will be add in that case. So delta IT equal to I1 minus I2. So what is happen, that in case if you subtract that thing, it will be remaining 2 RD AST ALOT sin intermediate frequency IFT plus delta phi. This component will be come your output side. Okay. So what is happen, this AS and AL2 is the amplitude of the signal, but we have the signal in the form of, we have to take calculation of that whole the cover area, how much the area will be covered. So we take every time in that communication system, that take the standard deviation or variance of that signal to calculate that amplitude of that signal. So what we have to take, that square root of the variance, it should be the PS for that signal for AST and PLO for that local oscillator signal. So in that place we have pushed PST and PLO in that case. Just that, so this will be your I2, I1 minus I2 in that case. And separately you calculate I1 minus I2 that from that matrix. Any doubt? Are you understand that? Akansa? Akansa, are you there? Akansa? Jagannath?
Yes, sir.
So why we use the polarization controller to match that state of incoming signal with the local oscillator signal. If there will be phase difference will be there, or both the signal will be orthogonal in that case, then it will we have the receive the zero, because they will be cancel each other that case. So we use the polarization controller, so they will be polarized with the same phase. So this diagram I have already explained. These things I have already explained. So balance detection for different photography has been developed for detection small difference in the optical power between two optical input signal while largely suppressing any common fluctuation of the input. So it will be suppress or diminish that noise, that thermal noise, short noise, flicker noise, whatever the noise, expressive noise, it will be dismissed by only that balance detection, because we use the 2 into 2 coupler. So we divide that two signal into E12 and E22. So we cancel that noise on that E12 side and E2 side, and then we have to subtract that. So this intermediate frequency will be very less in that case. That phi LO should be very minimum in that case. So second questions, that why phase log loop is used in the coherent heterodyne receiver. And why phase log loop is not necessary for 90-degree hybrid? Anyone can answer that? This should be will be same, and that balance detection. Just we have take one feedback loop from that PLL used in the homodyne receiver. So in that case, phase log component, we have another phase, that phi and t in that case. So this phi and t should be that phase varies as a function of time due to the phase noise signal and a local through the and local oscillator. So we have the same component I1 and I2 equal to RD AST ALO sin omega phi plus omega ST, but there is a one phase component that will be come due to that phase log loop feedback through output of that detector. That so
Sir, it is based on the phenomena of backward scattering also.
yeah,
Sir, it is also based on the phenomena of backward scattering.
not the backward scattering, just whatever PLA will be compared with your that signal with the local oscillator signal. We have that noise from noise, that phi will become from where? Some extra component will become through the local oscillator signal, through that only. So what is happen? We put the one phase log loop through the output side. We have to compare with that input signal with that output of the signal, and then we suppress that noise in that case. So it will not a back scattering, that I2 component or that IT component of that outside of that our balance detector. We just compare that signal with that local oscillator signal, that, and we compare the phase, amplitude, and frequency of that local oscillator through the phase log loop only, that. So what is happen, that in this way phase log loop we used to take the low frequency phase noise. There is a very low frequency phase noise which cannot detect out at the output side of that, and it will affect our signal on that detector side. So what is happen, through with that we comparing through that phase log loop, we correct that and we make it that phi and t equal to 0. Understand?
Yes, sir. Yes.
So just we want to suppress that noise or extra component come through the local oscillator. We want to make it the 0. So we use the phase log loop in that case. So phase log loop, you to track the low frequency noise apply to that phi and t equal to 0. This is the diagram. So there is the one is that this is the parallel signal will be go this side. This is the parallel signal. So local oscillator will become combined with that PBS, and this is that perpendicular signal will be go through that coupler. So we have used there 2 into 2 coupler. This is the ES2 signal will become have the omega ST is the phase is the frequency. Here omega L is the frequency, and both are here I1 and I2 will be combined that signal that previously that phase detection. So we use the two balance detection here, and this will be one is I1 square 2 and I2 square, and this low pass filter to pass that low pass signal that we have to suppress here only pass that signal. So this is the power detection of that low pass signal, and it will be come to that phase log loop, and it will compare with that signal that we have to feed back to the local oscillator. Through that we have to compare it that phi and to make the through the 0 in that case. This is that diagram of that 90-degree hybrid. So this is the equation of the balance detection. We have this the quadrature equation, and that one is that in phase equation and quadrature there is difference, because due to this 90-degree we have got the one component at quadrature. So what is happen, this is the 3 dB coupler that combine that signal. This is also 3 dB coupler. Okay, so what is happen that one signal will be go through that this signal is the ES by root 2, and this signal will be one imaginary component J component of the ES by root 2. Same component at EL by root 2 come here, and J component EL by root 2 come here 90-degree. And what happened that this is the 90-degree, so it will be change the phase to minus EL by 2. These are both are in the opposite phase, and this JS2 and the ES2 by will be combined here 2 into 2 coupler, and there will be signal one E1 2 and E2 that have the current I1 2 and I2 and I3 and I4. So what is happen that you know that E1 ST signal equal to, we have to already explained that AS1T into A ki power G t, ELO2 ELO2, and phi S2 should be that phi should be phi S minus phi LO. So that component we have to matrix that E1 and E2 matrix. If we explain, it should be 1 by root 2 into 1 by root 2, one imaginary component J and 1, and that EST signal and EOT signal. So what is happen, it will come onto 1 by 2 or take the mode of that square, and this is the EST plus EJOT ELOT plus JEST signal. So this is in that one component that minus in the second component E3 and E4, because that ELO will become in the 90-degree positive in case. So what is happen that this component will become that ESGST and ELOT in the E3 and E4 equal to minus EST and ELOT, and if you multiply both the signal, then you have to get the I1T and I2K in the quadrature current, and that bottom band current, that in phase current in that case. So one current here is that see that this is the sine component and this is the cos component. So this sine component, due to that 90-degree shift of that noise that in that case, so we call we have the opposite phase in that case of the signal, and it is a in phase amplitude is the cos component in that case. So in phase and quadrature component of the signal we generated due to that 90-degree hybrid model. Any doubt you can ask that. Class, Akansha. So we have calculated that imaginary component in the separate case and in phase component in that separate case. So what is the disadvantage? There is a two problem in that 90-degree phase degree hybrid. Why we phase log is not necessary for 90-degree phase component, since both in phase and quadrature component are extracted simultaneously, because we extract these are from that the one phase from this and this component. But in case of that homodyne, we calculate through that one single component, so we have to take that feedback loop. So there we need a PLL, but we do not require a PLL. So phase noise component needs to be carried out, frequency offset correction need to be carried out. So there is a two merit. This merit is that one is there is a phase component that phi s will be included in this case, and one is the intermediate frequency component. That should we will have to minimize through some algorithm use, and that ma'am already explained some demo, some code will be explained that how you minimize that through that consolidation diagram of the QSP quadrature phase amplitude, or the 60 QMA diagram. So that DPS detection phase of system, we have algorithm chart will be explained in that video, in the madam video. Through that we can correct that our constellation diagram through that. So list the common source impedance in the transmitter receiver in the coherent system. What is that common demerits of that in the transmitter receiver in the coherent communications? Anyone know that? So one is the phase noise. We have receiver, the receiver side, a detector. So what is the this is the phase noise of that component. So this is the consolidation diagram of that quadrature phase amplitude. There is a four phase, that 1 and 2, and what is that nearest by angle difference will be 45 degree for QAPSK and around 60.98 for 16 QMA. So phase noise is modeled as that for delta k equal to I equal to 0 into k and phi delta phi a, where delta k is the phase added to the kth symbol. So if we have the symbol 1 2 3 0 and this is the k, so this will be NRZ type of the signal will be returned to 0 and not returned to 0. That signal 1 0 1 0, that signal will become in the input side to that quadrature phase modulate side. So phi is that ideal Gaussian random variable with the zero mean and variance square. So this is we take the variance of that signal, that 2 pi delta f by ts. So is the combined line width of the laser delta f and ts with the symbol time. So if we have the signal is that ws and it has the symbol time ds, and one signal will be that some delta if or that intermediate of signal in that and we have the we have the combine, and the phase margin should be that difference between that 45 degree calculation. So what will use that, either we use to increase that line width of the signal, this should be more, we can avoid that phase noise in that case. Line width due to the frequency fluctuation, some there is change in that frequency, that ws equal to delta w equal to ws minus wlo. So it will be decreased or increased due to the frequency fluctuation. So we can minimize that line width of that signal, through which we can cancel that phase noise. Add undesirable phase pre-distribution in that case. Another impedance is the frequency offset. So adding the phase every time it in the frequency. So whatever that phase noise, it will be that in every time that 1 0 it have another phase noise, then 0 have the another phase noise, 1 have another phase, it in the whole component it will be add the phase noise in the signal. Additional source is that so this is the phi and t, that phase noise is added by that phase noise 2 pi fd and ts. N is the number of symbol, ts the time, and fd that fluctuation in that frequency is that. So fd should be the ffx minus frx. So if there is a two signal, one is that input signal and frx signal. So we have to take that difference, that how much the difference that fluctuation from that center frequency. it will give that 5D. So it will happen due to the phase noise in the signal, in every bit of that signal added by every time. Another is that intermediate in phase and coordination imbalance, bandwidth limitation at the receiver and transmitter. We have some limitation there. We have to only that 60 gigahertz bandwidth or 64 100 gigabytes bandwidth. But due to that limitation, we have to this common source error will be received at the detector side. List the common source impedance in the channel of the coherent communications. In channel, what is that signal will be disturbed in the channel? Can you tell anyone me? So in a channel we have the chromatic dispersion due to the fiber material or that intermodal or intramodal polarization mixing, that due to the non-linearity case of that fiber four-way mixing, polarization mode dispersion, that single polarization mode or some other modes, that chromatic mode or this will be happen, and non-linear effect in the fiber. This will be responsible for the source impedance in the channel in the current communication. So these are four components will be responsible for that common source. How is a CMA algorithm modified to compensate for the polarization mode dispersion? So use multiple tap filter in place of the single tap filter, through which we can modify that polarization mode dispersion. We can modify it in the CMA algorithm. One question is for you for practice assignment. So you have to calculate that accumulated phase over 10 to the power 10 symbol due to the frequency offset of 2 phase hertz in the 10 gigabit of the QFSK system. So you have to calculate delta phi n. So this formula I have given 2 phi f d and ts. Okay. So n is you have to given that 10 to the power 12 symbol total, frequency you have to given, 10 gigabit of bandwidth you have to given. So ts should be equal to 1 upon 10 into 10 to the power 9 gigabit, and fd you have to given that 250 into 10 to the power 6. You have to multiply about 25 with that signal if you calculate for the one symbol fdt, and if you multiply with the 10 to the power 12 into that this component delta phi n, you have to calculate that total accumulated time in that case. Any doubt? Akansa, are you there? Akansa? Jonek?
Yeah, I'll share a PPT.
Okay.
Just the first question, I'm giving you the solution. I probably should have changed something. So in the first question, this what does a 90 degree hybrid do? That is given as this transfer function, this one, and this input signal electric field and local oscillator electric fields, they are given like they can be expressed as these terms. That is also given. So you use these two information. So for E1 and I1, I'm giving you the solution. So E1 will be like matrix multiplication out of this first row. So 1 times ES plus e raised to the power j pi by 4 times ELO. And what is the photodetector current? It will be like responsivity times mod E squared. Because these ES, ELO, and also this all of those are complex terms, complex numbers. So we will find the mod square value as e1 and e1 conjugate multiplied. So this is where I think the doubts are, if there are any. So uh, what we will do is we will use this information that AS is only real, it only has amplitude, and the phase is completely specified using this. Maybe this phi s also has some noise, like you can consider later. But like this is the general form. So substitute this back to this I1 expression. So I1 is some RD times these two square root terms I just collected as this 0.5 for now, and then one is just E1, that is this term, just as it is ES plus this term, and its conjugate. So its conjugate will be just this conjugate of this term, conjugate of the LO term, and also the conjugate of this e to the power j pi by 4, we can minus j pi by 4, that's all. And then we collect. So ES times ES conjugate will come as this mod square of ES, which is also this AS term, because these phase terms will just cancel, that's all. Similarly for ELO. And then there will be these two terms, like multiplication of ES times this e to the power minus j pi by 4 times ELO conjugate, that is this term. And similarly another term for this multiplication, which is this term. And then just substitute all of the, like, what is the definition of ES. So instead of, in terms of just the, this is basically converting to a polar form, you can say. This is just the magnitude and just the phase. So then you write ES as just AS times this definition. This is the ES term. Then ELO conjugate. So this term, and here instead of plus it is minus. Your phase got reflected, that's all. And this e to the power minus j pi by 4 is just remains. Similarly, this other term will have like ES conjugate will come like this. ELO remains as it is, it will remain like this, and it put j pi by 4 becomes j pi by 4. Here you can see that if you collect all of the phase terms, j to the power omega s t plus phi s minus omega LO t minus phi LO minus pi by 4, and all of the phase terms in the other term will be just negative of all of those. So instead of plus omega st plus phi s, will be minus omega s minus phi st. So here you will use this definition of this cos theta. So this is what you will use, and this is how, why these two terms can be collected. These two terms plus this 0.5 multiplication factor also. So this will come as the in the form of some constant AS times ALO terms, AS times ALO times e to the power j theta plus e to the power minus j theta by 2. So you collect all of these, and theta will be the omega s minus omega LO. We have substituted as omega IF by definition. Phi s minus phi LO, we have substituted as delta phi. And minus pi over 4 just stays this minus pi over 4. This is the like first part of the first question. This is the first question, and I think second question is just a similar for E2. You repeat. For the 3 by 3 case also, you're only considering the first two terms of the 3 by 3 matrix. So you will take only this first two terms, and equations will come just like this, but these factors will be different. These factors will be different. There will be some amplitude also in front of this ES and ELO terms. That's all. That's how you proceed. And for question 3 and question 6, they're asking you to find I1 and I2 you find, and they're asking you to find I1 square plus I2 square. That's all. There will be some uh, there will be some trick like cos square plus sine square is one that will be used. I cannot give you in more detail because these are going to be evaluated. Right? I cannot just solve everything, but I don't think you should have much problem. And for 8 and 9, you just compare the signal powers because noise comes after. We are only like photo detector you read properly, so you know what is the current falling. Noise power will depend on this. Just consider thermal noise limited system, and noise power will remain constant if the bandwidth is not changing. That's all. Don't use your brain too much. And in case you want some more detail, sorry, this is also a good textbook. You can write down the name of the author if you want. I don't know if it is listed in the course page. But, when in doubt, on top of Agarwal or Kaiser, you can also check this book. This is more recent, so Kaiser and Agarwal are like ancient books. They're good books, but for more recent advancements, you can also use this as a reference. That's all. Akanksha, I hope it is. I1 square plus I2 square.
इन्होंने पीछे देखा, मैंने तो क्या है बाहर को दौड़ा, मैं फोन किया तो गाड़ी में जब गया
So this term will remain constant. And cos square you will have something like
शिद्दत हो रहा है क्या?
ऐसे खड़ा होना, सीधा खड़ा नहीं हो जा रहा
what is not working, so I have to type.
वो उस केस में होता है, इस सल्फर में नहीं होता.
किस केस में?
डाइमीटर डाइसल्फाइड.
So basically,
कल मेरा भी डाइमीटर डाइसल्फाइड करोगे तो होगा. इसमें नहीं होता. ये नॉर्मल सब, इसमें बहुत कुछ इम्प्रूव और ईयर में जा रहा डायरेक्ट.
मेरे को सांस लेने की दिक्कत हो गई. वो बस में 2 मार्क्स लगाए थे, तब ये बात अगर मैं ऐसे बैठा तो मैं बाहर को दौड़ा के वो ऐसे आया कहता सेंसर बचाने के लिए बुला रहे, मारने के लिए मुझे ना
ये कौन कॉल कर रहा है मुझे बार बार? तुम कॉल कर रहे थे सुरेश? हाँ?
so it will come something like this, which will in turn you can express this as some other angle. And here I use here you're supposed to use this this is how the sums will collapse. Like, this will remain as some cos square, and this will just become some sine square. Cos square plus sine square equal to 1. And for SNR, I think some previous weeks had covered this photo detector part, but here consider noise power to remain the same, and signal power is just I you have it, the resultant. This is a signal, that's all. Not this, like I1 square plus I2 square is the quantity that you are supposed to calculate. So that is your signal, that result. Answers from question 3 and question 6 are your signal powers, detected powers. You just compare it with whatever you need to compare it with. I cannot directly give you an answer right now because assignments are graded, right? So I cannot solve it for you. You are supposed to understand and then solve it, right? You can always ask in the forums or rewatch the videos if you are having some doubts, or you can also check the textbooks. I mean, they are available as ebooks. Yeah. Can you believe that? Yeah, sure. We have the Google Classroom, and also on top of the course page there is a Ask a Question button. If you click on it, it will take you to a Google group. Earlier I did not have notifications for the Google group, but now I have it. You can ask there. Or my email is, I think, is it this? Yeah, my email is this. It's Google. Let us not meet on Tuesday. Next Sunday, same time we can. Next week is easy, I think. Just geometry and stuff. And the assignment should be easy.
Any doubt? So the next same time or same day we will meet to.
Yeah.
So next Sunday we will meet on the same time, 5 to 6 p.m. Meanwhile, you can put your doubt and that on that ask two questions or Google forum if you have any doubt from like week 1 to week 12, because it is the last session we have to conduct it on that Sunday, that on 16, 15 or 16.
Yeah, 16 actually.
Yeah, so be prepared with your doubt from that week 1 to week 12. So
Sir, we can house all the doubts of week 1 to week 11.
yeah, sure, no
in
problem. Just before you
Okay.
just put on that ask to form or that Google Classroom, so we can take that solution of that doubt.
Okay, sir.
So we can prepare that according, because this is the last class, so we cannot excuse that we will see in the next class or anything there. So
Yes.
you have the whole week for your doubt. So whatever have you doubt, you can put that on Google Classroom or ask to form that. If possible, we can respond immediately, and if need to understand, then we can include in our slide there. Is it okay, Jonek?
Yeah.
So thank you. Should we close session?
Yeah. That's
So thank you everyone. So we will meet on that Sunday again. Thank you so much.